In section 4, we talked about sampling distributions for sample means, and in section 5, we're going to discuss sampling distributions for a difference in sample means. So similar to when we were talking about proportions, we'll have two populations or treatments that we're looking at. We'll have two parameters, two statistics, and two sample sizes. So population 1 and 2, we have a mean 1 and a standard deviation 1, mean 2 and standard deviation 2. We have an x bar 1 and sx 1, x bar 2 and sx2, and then n1 and n2. Now our sample sizes could be the same, but they are not required to. They should be close to each other if they're not the same. So when we're talking about the shape, center, and spread for a difference in two means, similar to proportions, both means have to be normal. So if both population distributions are normal, then the sampling distribution of x1 bar minus x2 bar is normal. If we don't know that the population distributions are normal, then we can't say the sampling distribution is approximately normal. So each sample size would have to be large enough. So n1 would have to be greater than or equal to 30, and n2 would have to be greater than or equal to 30. For our center, we have to make sure that we have two random samples, or we have randomly assigned to two groups if it's an experiment. And as long as that condition is met, we can say the mean for x1 bar minus x2 bar is just the subtraction of each sampling distribution's mean. So mu of x1 bar minus mu of x2 bar. Very similar to proportions. The spread is going to be a little bit different. So we have to check that the 10% condition is met for both sampling distributions. If you're performing an experiment, you don't need to check independence because by definition an experiment has independence already in it. So our formula for spread for the difference is very similar to when we were looking in section 1. So I'm going to have the square root of the standard deviation of population 1 squared over n plus standard deviation of sample 2 squared over its n. It's very similar when we were looking in section 1 and we squared our standard deviations, added them, and took the square root. But this time, because we aren't looking at 1, we have to account for the sample sizes. So we're going to do a couple examples. So in our first example that we have the mean height of 15-year-old boys in centimeters is 175 and the standard deviation is 8. For girls, the mean is 165 with a standard deviation of 8 as well. If 8 boys and 8 girls were sampled, what is the probability that the mean height of the sample of girls would be higher than the mean height of the sample of boys? Verify that you can construct a sampling distribution for a difference between sample means. So the first thing I have to do is label x1 bar and x2 bar. So I'm going to have x1 bar be my boys and x2 bar be girls. Okay. So I am looking to find the probability the mean height of girls would be higher than the mean height of boys. So that determines my probability statement. So I'm going to look at the probability that x1 bar minus x2 bar is less than 0. Since girls is x2 bar, their difference would be negative if girls were taller. Now we're going to check our conditions. So first I'm going to check random. So it doesn't specifically say random. It said 8 boys and 8 girls were sampled. We'll just go ahead and assume they were sampled randomly. For independent, both of my sample sizes are the same. It's 8, so I don't have to check it for both. 8 is less than or equal to 10% of all boys. And then 8 is less than or equal to 10% for all girls. And there's at least 80 15-year-old boys and girls, so we're good there. Then the last one I have to check is normal. Now, it doesn't specifically state here that the population distribution is normal, but we have done plenty of examples in the past where we look at average heights, and we know that those population distributions are normal. Because our sample sizes are 8, they're not greater than or equal to 30, but in general, heights are normally distributed. So now I can calculate my mean of my sampling distribution, which is going to be 175 minus 165, which is going to give me 10. Standard deviation is 8 squared over 8 plus 8 squared over 8, because we have the same standard deviation for both, and we have the same sample size for both. And we're going to get a standard deviation of 4. So my z-score, I'm going to do 0 minus 10 all over 4. And we get negative 2.5. So when I go to normal CDF, my lower bound is going to be negative 1E99. My upper bound is negative 2.5. Mean of 0 and standard deviation of 1. And we get 0.0062. So that tells me the probability, the height of girls is higher than the height of boys is 0.0062. So it's very, very unlikely that the sample of girls is taller than the sample of boys. Last example, we have an electrical appliance made by Company A has an average life of 2,500 hours with a standard deviation of 500 hours. Company B makes this appliance with an average life of 2,300 hours and a standard deviation of 800 hours. We take 300 Company A devices and 200 Company B devices, calculate the probability that the average life of the sample from Company A isn't 100 hours more than the average life of the sample from Company B. So I'm going to have X1 bar be Company A and X2 bar be Company B. So we're looking at the probability that the difference, so if we look in our statement, we want to know average life from Company A isn't 100 hours more than the average life from Company B. So we're looking that their difference is less than or equal to 100. So I'm going to check random. And again, we're selecting them randomly. Independent, we have different sample sizes and different populations, so I have to check. So we've got 300 from Company A, so that has to be less than or equal to 10% of all Company A appliances. And then 200 has to be less than or equal to 0.10 of all Company B appliances. And we can go ahead and say they make at least 3,000 and 2,000 at each. Okay. And then lastly, normal. So we can't assume a normal distribution here, so we have to check our sample sizes. 300 is greater than or equal to 30, and 200 is also greater than or equal to 30. So we have a normal distribution. Okay. So I can now calculate my new mean and standard deviation. And we're going to have 2,500 minus 2,300, giving us a mean of 200. Standard deviation is the square root of 500 squared over 300 plus 800 squared over 200. And we get 63.51. So for my z-score, we're going to do 100 minus 200 over 63.51. And we're going to get negative 1.57. So for a normal CDF, our lower bound is negative 1E99, upper bound negative 1.57, mean of 0, standard deviation of 1, and we're going to get 0.0582. So the probability, the average life from company A isn't more than 100 hours than company B is 0.058. So also very low probability, which means it's probably likely that the average life from company A is 100 hours more than company B. Okay. Let me know if you have any questions about differences in sample means.